Hello everyone, my name is Bjarne Heyer. I'm a master's student at Göttingen University and I'm going to talk about sediment deposition dynamics in a high altitude lake system in the northern Ecuadorian Andes. And here you can see a picture of my study area, the Laguna Coricocha, a caldera lake, which is situated around about 35 kilometers north of Ecuador's capital city, Quito, in the tropical Andes. The lake is located at 3,716 meters above sea level. It is oligotrophic, has a high visibility, and is slightly alkaline. And it has a surface area of around about 3 square kilometers and a maximum water depth of 118 meters. The catchment, as you can see on the picture, is characterized by steep slopes. It is a small catchment which is covered by paramo vegetation and some remains of polylepsis forest. The sediment core was taken at the western flank of the lake, as you can see on the upper map, at a water depth of 24 meters. The tropical Andes are considered as globally relevant biodiversity hotspots, and carbon sinks in this lake in particular is also relevant for the local water supply. And all these factors make such lake systems really interesting to study. So what are the drivers of sediment deposition in such a high altitude lake system? In order to answer that question, I am using a multi-proxy approach, including XRF core scanning, magnetic susceptibility, CN and grain size analysis, as well as 14C dating and tephrochronology for the age frame of the sediment. And the data I further analyzed using multivariate statistical approaches. So let's have a look at the sediment core. It is 72 centimeters long and covers a time range of 3,000 years, calibrated BP 14CH. As you can see on the left side, you can also see some dates of already analyzed tephra layers, which also helped to create a time frame. The sediment can be visually characterized and divided into three main units. We have this dark brownish background sediment material intercalated by several tephra layers, and then we have a coarse-grained event deposit at the base of the core. And now to further analyze the difference between these layers, we will have a look at the geochemistry, the XRF data. So you can see that we made a cluster analysis based on the plotted element intensities of the four elements: calcium, iron, potassium, rubidium, and the incoherent-coherent ratio. And regarding the element intensities, it is really nice to separate the event layers because they have very remarkable peaks. For example, the tephra layers are characterized by peaks in potassium, rubidium, and also the magnetic susceptibility, as well as low values in the incoherent-coherent ratio. Same goes for the high energy event. It is also really nicely visible in the data. We have here elevated magnetic susceptibility, calcium and iron values, and low values in rubidium, potassium, and incoherent-coherent values. So it's really nice to see the event layers reflecting in the data. However, these strong signals also superimpose the signals of the background deposited material, which is actually or eventually more interesting for the environmental reconstruction. Let's have a quick look at the principal component analysis. So here again we have our 5 clusters. Especially cluster 1, 3, and 5 separate very nicely. We have the upper sediment layers associated with this cluster 1, which is interpreted as organic rich sediment input, or sediment, organic rich sediment. We have cluster 3, which clearly shows our tephra input, and we have the cluster 5, the high energy event. In between these clusters, we can find cluster 2, which seems to be has a mixed signal somewhere between organic rich and the tephra sediment, which I interpreted as detrital input sediment mixed with tephra material. And then we have our cluster 4, which is considered as reworked, lake internal reworking of tephra material without a lot of organic rich material. And I also tried to interpret the components. Component 1, which is which accounts for 57.4% of the dataset's variance, shows an increase in tephra contribution, whereas component 2 shows a decreasing contribution of volcanic material. Now let's have a look at the grain size data and the end member modeling analysis, which is a bit more difficult to interpret, because as you can see on the left and the right side on the figure, that these end members, some of the end members have polymodal grain size distribution, making it a bit difficult to clearly identify single processes which are associated to those single end members. I still try to interpret it. So here we have end member 1 with its main mode in the fine silt fraction, which seems to reflect the calm water or background deposition. End member 2, also silt fraction, shows peaks at the distal tephra input from Kilotoa eruption, for example. Kilotoa is a more far away volcano from the Laguna Caricocha, and it also shows peaks which are considered to be catchment reworking. We have end member 3 in the coarse silt fraction, with also a mode in the fine sand fraction. This end member reflects tephra material and also the in-lake reworking. We have end member 4 with quite nice peaks for the input of proximal tephra from the Cayambe volcano, which is not very far from the lake, and shows a direct input, no rework material. And then we have end member 5, the only end member which is really easily interpreted, as it has a major peak in the coarse-grained event layer. Yes, let's sum it up. The sediment core is characterized mainly by event deposits, volcanic event deposits as a major sediment contribution. We have low amounts of detrital and lake internal sediment inputs, which makes sense as the catchment is rather small, and we could see some reworking processes taking place, which have to be further analyzed. A problem with the data is that these event deposits superimpose the signals of the background material and thereby other environmental proxies. So next step would be to remove these event signals, which are shown here again as an example, to focus on the background sediment signals and possibly identify proxies of environmental or depositional changes. And another idea is to combine the results of the XRF and the end member modeling data. That's it from me. Thank you for listening.